Dear students, in the previous video that I posted in your group, I promised you to begin your video lectures from Monday. By uploading this video, I am fulfilling that promise. In this video, we will continue our discussions on the quantum theory of harmonic oscillator. In the last lecture, I have elaborated to you the importance of harmonic oscillators in physics. Here we are dealing with a simple harmonic oscillator. Still, it is very important because this is an exactly solvable problem. And many physical systems which are not simple harmonic can also be approximated to this. Now, after this, we went on to solve the Schrödinger equation for the harmonic oscillator using an asymptotic method. An asymptotic solution was assumed. Now, since this asymptotic solution was an exponential one, it was imperative that we add a harmonic term next to it. This is because the problem at hand is that of a simple harmonic motion. So it's important that there exists a harmonic term in the solution. After adding this harmonic term in the solution, we substituted this in the Schrödinger equation for wave function. And this has led to the appearance of Schrödinger equation being changed to that of a harmonic differential equation, the solution of which is a harmonic polynomial. It is from here we continue our discussions in an elaborate manner. So this is the Schrödinger equation after the substitution of the asymptotic solution. This equation is of the form of a harmonic differential equation, and it's reasonable for us to assume a power series solution for this. This solution can be written as hy equals summation n equals 0 to infinity a n y raised to n. Let this be equation 9. Here a is the coefficient. Now we have to substitute equation 9 in equation 8. For that, we have to first determine d square h by dy square and dh by dy, which are the second and first derivatives of hy respectively. Now dh by dy equals summation 0 to if we differentiate this, we will get n a n y raised to n minus 1. Now this dh by dy has to be differentiated with respect to y one more time to obtain d square h by dy square, and this will be summation 0 to infinity n into n minus 1 a n y raised to n minus 2. Now we have to replace the d square h by dy square and dh by dy in equation 8 with these summations, these power series, and in that case we will get equation 8 as summation 0 to infinity n minus 1 into n a n y raised to n minus 2 minus summation 0 to infinity 2y into n a n y raised to n minus 1 plus lambda minus 1 summation 0 to infinity equals 0. Now this equation can be slightly modified by rearranging the terms as summation n equals 0 to infinity n minus 1 into n a n y raised to n minus 2 plus summation a n lambda minus 1 minus 2n y raised to n. Let's label this equation, this is n. Let's label this equation as x1. Now in order to determine the coefficients a n, we have to first expand both these series. Let's expand the first series. Then when n equals 0, we will get this term will be 0, so it can be written as 0 plus. For n equals 1, this will be again 0 because n minus 1 will become 0. Then when n equals 2, this will be 2 minus 1 into 2, that is 2 a2 pi raised to 2 minus 2, which is pi raised to 0. And similarly for n equals 3, we can write 6 a3 y raised to 1. And when n equals 4, the term we get is 12a4 y square, and this will continue. Now we have to add the second series. Let's see how it expands. When n equals 0, we have a0 into lambda minus 1 y0 y raised to 0. And when n equals 1, we get a1 lambda minus 3 y raised to 1. And when n equals 2, we get a2 lambda minus 5 y square, and this will continue. And in the RHS you have 0, which you obtain from this equation. Now let's pair up. Okay, now let's pair up the coefficients of powers, same powers, in that case of same powers of y. So the coefficient of y0 will be 2a2 plus a0 lambda minus 1 into y0. Now the thing is that if this equation is to be true, that means the sum of these entire terms will give you 0. Then each powers, the coefficients of each powers of y should be separately equal to 0. That's the idea that we are using here. So we have paired up the coefficients of y0, and this can be greater to 0. And now the powers, the coefficient of y will be 6 a3 plus a1 lambda minus 3. Square brackets, that will be equal to 0. Now the coefficients of y square will be 12 a4 plus a2 into lambda minus 5 y square equals 0. Proceeding similarly, the coefficients of the nth power of y will be k plus 1 into k plus 2 ak plus 2 plus ak lambda minus 2k minus 1 into y minus 2. You can verify this. This is a general equation, and you can derive these three equations from from this equation by changing the values of k. Let's label this equation as x2. From this equation we can determine the relationship between ak plus 2 and ak. The relationship between ak plus 2 and ak will be ak plus 2 equals 2k plus 1 minus lambda divided by k plus 2 into k plus 1 ak. So you will be able to express the k plus 2th coefficient in terms of kth coefficient. Now let's try to find out A2. So in order to find A2, you should give k a 0. Then you will get A2 equals, since k is 0, this term vanishes. This will become 1 minus lambda divided by 2 into 1. That is 2 into A0. So you are determining A2 in terms of A0. Similarly, we can determine A4 by substituting k equals 2 in this equation. So here we will get k plus 2, which is A4, and now in this term we have A2, and A2 can be replaced using this equation. This term can substitute A2 here, and you will eventually get your A4 in terms of A0. So you can obtain the entire even coefficients in terms of A0. In a similar manner, you can obtain your odd coefficients in terms of A1. That is, the first thing you have to do is put k is 1. Then this will be A3. So A3 will be obtained in terms of A1, and similar to what we have done for the even coefficients, we can obtain the entire odd coefficient series or set of entire odd coefficients in terms of A0. Now the problem is that your solution will have all these coefficients, odd and even coefficients, but if you put A0 equals 0, then it's obvious that all your even coefficients will vanish, because they are all written in terms of A0, a factor multiplied by A0. So they will all vanish, and your solution will only have odd coefficients. And if you set A1 equals 0, then if A1 is 0, then you will only have your equation will only have your solution will only have the even coefficients. So you will get two independent solutions. The first one will be HE, where E stands for even. You will get this when A1 equals 0. This will be A0 plus A2 y square plus A4 y etc. This is obtained from your equation 9, where you have expanded the power series and removed all the odd coefficients of the series. And similarly, we will have if the odd coefficients, the even coefficient vanish, then we will have H0 a1y plus a3y square plus a5 y raised to 4. So y raised to 5 plus etc. This can be written as y into a1 plus a3 plus a5. So this is your even solution, this is your odd solution, and this will be y into a1 plus a3 y square plus a5 y raised to 4 plus etc. These are independent solutions. Most of the times a linear combination of these two solutions would be considered as an ideal solution for harmonic oscillator.